Welcome to our regular subscribers and viewers, all 5 or 6 of you. And welcome to anyone else who has come upon this video. I am David Beams. I'm Associate Professor Emeritus of Electrical Engineering, and this is another video in the series Electronics, the Story of One Human Lifetime by David Beams and Gary James. Today's subject is what I call bonus circuits, part 2. These will be circuits that are implemented as simulation circuits in LT Spice, available for you to download and experiment with, and little explanation of how they work. And today I'm going to be talking about using the bipolar junction transistor in temperature sensors. But first, let's consider the cruel fate that has befallen the bipolar junction transistor. There was a time when it was the transistor. And to be more specific about this, I'm making this recording in August of 2023. Let's go back 50 years to August 1973. I was an engineering intern working that summer, and in less than a month, I was going to be back at the University of Illinois at Urbana-Champaign to start my last semester as an undergraduate in the electrical engineering program. And at that time, the bipolar transistor was the transistor. It was ubiquitous in analog ICs, operational amplifiers, voltage comparators, the like. And it was the basis for the dominant digital logic families of the day, particularly TTL, or transistor logic. And it was also used in high-speed logic, a form called emitter-coupled logic, or ECL. Now, the field effect transistor, it had been invented and was finding its way into electronic design. It came in 2 flavors. One was the junction field effect transistor, or JFET, and the other was the metal oxide semiconductor field effect transistor, or MOSFET. Now, the JFET seldom appeared in integrated circuits. The only integrated circuits that I can think of off the top of my head that used JFETs were a line of operational amplifiers in the TL0, 6, 7, and 8 families that Texas Instruments introduced in the 1970s. It was most often found as a discrete component, and it has largely disappeared from electronic design in the years since then. Now, RCA introduced its CD4000 line of CMOS digital logic in 1968. It featured rail-to-rail output voltage levels and excellent noise margins, but it was limited to low-power, low-speed applications. Cutting edge, but not well known. As a matter of fact, in the fall of 1973, I was interviewing for a job, and one of the engineering managers takes me out to see the production facility. And as we go out into the shop, he turns to me and says, "All of our new designs are state of the art. All of our new work is being designed with CMOS." And I remember thinking, CMOS, that grows on rocks at the seashore, right? I mean, I hadn't heard of it. But I figured, I'm not going to say what is CMOS and, let him know that I don't know. I figure, try to get the job and then find out, which is what happened. But anyway, today, though, however, there's been vast technological progress in the intervening years, and the MOSFET is by far the dominant transistor technology today. And BJT still hanging on in legacy designs, but it also has some unique applications, which is what we're going to look at here. Let's consider the relationship between absolute temperature and the base emitter voltage of a bipolar transistor at a fixed collector current. Like this, we have a current source that's forcing a collector current and an appropriate base emitter voltage that's producing that collector current. And the relationship between the collector current and the base emitter voltage can be summarized simply by this equation. which I is equal to I sub S is a parameter called the scale current, and it comes out of the Ebers-Moll model of the transistor. And I'm not going to go into the derivation of the scale current in this particular presentation. But then it's multiplied by this term within the parentheses, which is an exponential term minus 1. And generally speaking, the exponential is much larger than 1. So we can, for all practical intents and purposes, we can just simply drop the minus 1. And we have an exponential relationship between the collector current and the base emitter voltage. Now, again, I sub S is with the so-called scale current of the transistor. Q is the unit electronic charge. K is Boltzmann's thermodynamic constant with units of joules per Kelvin, and T is absolute temperature in kelvins. Now, we can find the base emitter voltage in terms of the scale current and the collector current. Little mathematics, very simple. So the base emitter voltage is equal to KT over Q times the natural logarithm of the collector current divided by the scale current. And the physical constants K and Q, their ratio is 86.17 microvolts per Kelvin. So just looking at this equation, one would think that VBE would increase linearly with temperature. However, you may also know that there's a rule of thumb that the base emitter voltage of a bipolar transistor or the forward voltage of a silicon diode, typically that voltage decreases by 2 millivolts per degree Celsius. Of course, remember that a degree Celsius has the same magnitude as a Kelvin. So anyway, how do we resolve this? Well, let's do a simple, let's plot the base emitter voltage versus temperature for this simple circuit in which a current source fixes the emitter current of an NPN transistor. And assuming that the transistor's current gain is quite large, the collector current is virtually the same as the emitter current. So we can say this is operating with constant collector current. And we do a temperature sweep with LT spice of this simple circuit. And this is a plot of the base emitter voltage. And you can see it does decrease. As a matter of fact, it's very close to minus 2 millivolts per degree Celsius. So why does it do that? The answer is that's because of the strong temperature dependence, the exponential even, temperature dependence of I sub S. The scale current rises very rapidly with temperature. That's why the base emitter potential for a fixed collector current goes down. Now, you can make a thermometer using either a BJT or a diode as a temperature sensor and exploit this phenomenon. The problem with so doing, however, is that you're sensing small changes in voltage, minus 2 millivolts per degree Celsius, but it's sitting on top of a large DC offset, typically like at room temperature, typically for a silicon PN junction, 600 to 700 millivolts. Can be done. It's not the easiest thing to do. There are better ways to make temperature sensors with bipolar transistors. Let's look at those. Here we have another structure in which we have an asymmetric differential pair. That is, we have the original transistor, but now we have another transistor, which is actually a composite of N transistors, each of which is identical to QA. And we're going to presume that the same collector current is flowing in both this transistor and the composite transistor. Now, we've seen before, the base emitter voltage for transistor A is KT over Q times the natural logarithm of the ratio of collector current to the scale current. But the base emitter voltage for the B transistor, the composite, is KT over Q times the natural logarithm of I divided by N times I sub S. That is, having N identical transistors in parallel gives me the same effect as one transistor with a scale current N times larger. So if I find the difference between A and B, excuse me, VBEA minus VBEB, that's hard to say, you know? Anyway, delta VBE, there we go. VBEA minus VBEB is KT over Q times the natural logarithm of N. And this is wonderful because the delta VBE depends only on the absolute temperature T and fixed constants K, Q, and N. Wonderful. Well, let's see how we can apply this. Here we have bonus circuit 4 available for your download. We have an operational amplifier connected up to provide negative feedback, which will cause the voltages at both its non-inverting and inverting inputs to be equal, which means that the same current will flow in R1 and R2, which will be the collector current of Q1 and the collector current of this composite transistor Q2 through Q5. The difference in VBE, which I called here VOX, appears across resistor R3. And that voltage is KT over Q times the natural logarithm of 4. Now, in the next slide, we'll take a look at simulation results. But before we go there, I want to point out that this little 1 nanoampere current source was an artifact introduced for simulation purposes only. This circuit, this analysis that LT Spice will do is finding the operating point of this circuit over a stepped range of temperatures. One possible operating point for this circuit, at least numerically speaking, it's possible, is for the output voltage of the op amp to be 0 and the differential input voltage to be 0 and no collector currents in either Q1 or the composite transistor. In other words, it's drawing no current. In practice, the circuit won't find that particular stable operating point when you turn it on. So I introduced this 1 nanoampere current sink here to just unbalance this circuit just a little to make sure it doesn't find the 0, solution for operating point. Okay, so KT over Q times the natural logarithm of 4 should be 119.5 microvolts per Kelvin. And let's see how it works. Here's the simulation of that circuit. And the slope is 119.5 microvolts per Kelvin. It's linear and it's just like we predicted. This is wonderful. Here's an improved circuit. I call this bonus circuit 4A, and its difference is here, this resistive voltage divider. The difference in VBE appears across resistor RA. Now, if we neglect the base currents of the composite transistor, then we can say that the same voltage, or excuse me, the same current in RA flows in resistor RB. The current in RA is delta VBE divided by RA. Delta VBE is KT over Q times the natural logarithm of, in this case, 10, because I have a 10-to-1 ratio between the two sides of the asymmetric differential pair. And so the output voltage then is RB times that current, which gives us an output voltage of RB over RA, KT over Q times the natural logarithm of 10. Now, one important thing to note here is that the output voltage depends only on the ratio of RA and RB, not their absolute values. So this is wonderful because it makes this circuit suitable for implementation as an integrated circuit, because with an integrated circuit, it's not easy to make specific resistor values, but it is easy to make specific resistor ratios. And assuming that these resistors are of identical construction, their temperature coefficients should track, so the ratio of RB to RA should remain constant. Okay, so let's see how this circuit does. We're aiming with these circuit values for 10 millivolts per Kelvin. And it looks linear. And we got 10 millivolts per Kelvin. Remember, a Kelvin and a Celsius degree have the same magnitude. Anyway, 10 millivolts per Kelvin right on the button. Beautiful. Okay, now we can also make sensors using bipolar temperature sensors with bipolar transistors that provide current outputs that are proportional to absolute temperature. Here we have an asymmetrical differential pair with a ratio of 10:1. And here we have two PNP transistors that form a current mirror. Now Q12 here provides the base currents to the current mirror. It has very little, only a slight effect on the actual operation of the circuit. For a simple analysis, we're going to ignore the presence of Q12. We're just going to assume that the same collector currents are flowing in Q12, or excuse me, 13 and 14. So the difference in VBE appears across R1. So the current that's being drawn in R1 is, I didn't want to do that. The current that's being drawn in R1 is KT over Q times the natural logarithm of 10 divided by R1. That current flows through this side of the current mirror, Q14, but it's also mirrored to this side of the current mirror and flows through Q1. So the total current that's being drawn is 2 KT over Q log 10, natural log of 10, divided by R1. Now, in this case, the current that's being drawn does depend upon the absolute value of the resistor. So this is not a particularly good candidate for making an integrated circuit. However, sensors built on the principle like this one oftentimes will allow you to attach an external current programming resistor, which can be a metal film type of low temperature coefficient. Okay, let's see how this one behaves. This one should give us 1 microampere per Kelvin, and it looks pretty linear, and it's within 1.4% of the theoretical value. All right, now bonus circuit 5A. Well, that was bonus circuit 5 I just showed you. Here's 5A, and it's a variation on that same circuit. It's a variation of bonus circuit 5. What we've done here is we've expanded the current mirror, so there is effectively a third transistor, which is a composite of 10 transistors, each of which is identical to either Q13 or 14. Now, this composite current source also feeds current into R1. The current flowing in R1 is KT over Q natural logarithm of 10 divided by R1, but that current is divided among 11 of these PNP transistors, these 10 of the composite transistor and then Q14. And that current, that same current, is mirrored by Q13 into the collector of Q1. See, KT over Q natural logarithm of 10 appears across R1. Anyway, the total current that's drawn by this current source is 12 over 11, 1 over R1, KT over Q natural logarithm of 10. And with the resistor value I've chosen here, we should get 1 microampere per Kelvin. And it's linear and it's close, within about 1.4% of the theoretical value. Okay, so putting the wraps on everything, I've shown you how, in a fairly superficial form, how voltage sensors with outputs proportional to absolute temperature and current sources with output proportional to absolute temperature can be made exploiting properties of the bipolar junction transistor. So remember, the link that includes the access to the simulation files of this presentation, it's in the video description. And if you find these resources useful or intriguing, valuable, money would be good, but times are tight. In lieu of that, we'll settle for comments. So just remember, we appreciate your visiting with us. Keep those cards and letters coming. I am David Beams. It has been my privilege to be your presenter this afternoon, and I hope to see you again soon in another video from the One Human Lifetime Project.